as to continue slightly. And today the date is the 24th of April 2024. So remember, the topic is the thermophysics that we are looking at. And in our last class, we ended with the topic of, we ended at the calorimetry. I request that we all mute our microphones, please. I request we all mute our microphones. Those of us whose microphones are on, and in particular, is it Ignatius? Mute your microphone. The best is for you to settle down, sit down, and stabilize somewhere. Don't be busy doing other things while you are logged into the class. Chimuka Maumbi. I don't want to mute you. I want you to mute yourself. Chimuka Maumbi. Maumbi Chimuka, kindly mute your microphone. Oh, my God. Okay, so sorry for that disturbance. So in our last class, we ended with the topic of calorimetry, and we were saying that all situations which involve the mixing of systems or systems that are at different temperatures coming into thermal contact and exchanging heat is called calorimetry. And we did some examples of that. And today we are going to look at subtopic number 5, which is latent heat and phase changes. Latent heat and phase changes. Now, remember, when we were looking at calorimetry, we considered situations where systems at different temperatures when put into thermal contact. There is heat exchange. And this heat exchange leads to the fact that the hot system loses heat and the temperature reduces. The cold system gains heat and the temperature increase. So as you have seen here, there is a reduction and the increase of temperature. There is a reducing and increase of temperature. Latent heat and phase changes. We also have situations where this deals with a situation where exchange of heat does not lead to increase or decrease in temperature. It does not lead to increase or decrease in temperature. Rather, the substance changes phase, e.g., we can change from solid to liquid, and we call this melting. Or it can change from liquid to gas, and we call this evaporation. Evaporating. It can also change from solid straight to gas, and we call this sublimation. It is also possible that the change is actually from liquid to solid, and we call this freezing. We can also have from gas to liquid. Who knows what we call this? Anybody? When a substance is changing phase from gas to liquid, what do we call it? Anybody? We all passed grade 12, or we all passed from A level, O level. What do we call the change of phase from gas to liquid?
Condensation.
Condensation.
Okay. It is condensation. Okay, so this is the possible. So this happens at the constant temperature. Phase changes occurs at constant temperature. For example, freezing or melting happens at constant temperature. For water, it happens at 0 degrees Celsius. For other materials, it happens at different temperatures. The amount of heat that is required to change a given amount of mass. So we are going to define latent heat. Latent heat, let's add the word capacity. This is the amount of heat required to change unit mass of a substance from one phase to another. So the amount of heat required to change a unit mass of a substance from one phase to another is called latent heat capacity. And we use the symbol capital L to represent latent heat. Since there are two possible changes, heat, there is for each substance, there are two possible. This one or this one here. So there is no. I meant to talk about this one and this one here, not what I have indicated, not this. I want to talk about the possibility. There are three states, three phases. So I want to talk about this one and this change. So between these two, because of these two, we are going to have L V, which is latent heat fusion. This happens when the phase is changing from solid to liquid. Or vice versa. Then we also have LV, which we call latent heat of vaporization. This is the change of phase between liquid and gas, or vice versa. So the change of phase, therefore, will represent latent heat either as latent heat of fusion or latent heat of vaporization, depending on whether the change of phase is happening between solid and liquid or between liquid and gas. So the fusion comes from this and the vaporization comes from that particular one. Manager, I'll call back. Yes, I'll call back. I'm just in a meeting using the same phone. So that is latent heat of fusion or latent heat of vaporization, depending on whether we are changed to what we were discussing earlier. So what we were just indicating that latent heat is either latent heat of vaporization or latent heat of fusion. So here I meant latent heat of vaporization or latent heat of fusion. Which is liquid to gas, and fusion is solid to liquid, or vice versa. Mathematically, the statement that we just said here, this statement mathematically is given as in latent heat is equal to, latent heat capacity is equal to Q over M. And it is plus or minus. Plus when we are changing from, plus is the change from solid to liquid, or from liquid to gas. Then the negative is a change from liquid to solid, or from gas to liquid. So depending on which direction we are going, it will be a negative or a positive. So latent heat is either negative or positive. Therefore, the amount of heat that is required to change phase of a substance Q is given by plus or minus mass times latent heat. And latent heat is either V or fusion, whichever of the two you are talking about. So, what the general view of what we've talked about is that, for example, for water, the latent heat of we can have ice. Let's just give a general view graphically. So the graphical view of what we've talked about is that from, say, from negative 30, but you can go to any other negative number there. From negative 30, you can take it all the way to 0. If you add heat, it will go to 0. At 0, you have constant, where this part here, it is changing temperature. And we have the heat capacity of ice. We are using the heat capacity of ice. C of ice. Then here it is solid to liquid. And we have latent heat of fusion. Then from there, we can move from 0 all the way up to 100 degrees Celsius. When we reach 100, here we are having change in temperature of water. Here it was change temperature of ice, water. This is related to heat capacity of water. Then when we reach 100 degrees Celsius, we can have a flat line which signifies change in phase from water to steam. And this is associated with latent heat of vaporization for water. And then we can move again on from there to where we have a change in temperature for steam. Change in temperature for steam. This is associated with heat capacity of steam. This is how a graph of phase changes and temperature increases would look like for water. When we have water, we have such a situation where at 100 degrees Celsius, we have change of phase. At 0 degrees Celsius, we have this change of phase where the line becomes flat. Changes happen at constant temperature. Therefore, we can do a quick scenario where we can have different changes. Suppose we have, let's do a quick example where we have a block of ice at minus 10 degrees Celsius. Maybe let's say let's give it mass so that we can and we can have a complete question. A block of ice of mass 4 kilograms at minus 20 degrees Celsius is dropped in a bucket of water or in a bucket made of styrofoam made of styrofoam containing 7 kilograms of water at 27 degrees Celsius. Determine the final equilibrium temperature. Now, for me to be very, very sure of what I'm doing, let me increase the temperature to 87 degrees. Let me put the temperature of the water at 87 degrees. Then this way, I'm very sure of what I'm talking about. So, our assumption here, the situation we have is one where we have water. So I'm now moving there. We have a bucket of water, and it's made of styrofoam. And in here, there is water, and the amount of water is, as we have seen, 7 kilograms of water. This is water, 7 kg at 87 degrees Celsius. In here, let us drop a block of ice, which is 4 kilograms. This block is 4 kilograms initially at minus 10 degrees Celsius. The question is, find the final equilibrium temperature of the mixture. What is the equilibrium temperature of the mixture? This is the question. So, since water is at a higher temperature and ice is at a lower temperature, we expect that water will lose heat and temperature will reduce from 87 degrees Celsius to some final temperature. Ice will gain heat and temperature will increase from minus 10 to 0 degrees Celsius. Now, looking at the temperature of the water and the fact that the water has more weight than the ice at 4 kg, my assumption now and my best guess as an educated scientist is that not only will the ice increase its temperature up to 0, but I expect that after all the ice has become 0 degrees Celsius, I expect that the ice will continue receiving heat. It will gain again heat and change phase from solid to liquid to become water. That's what I expect. And then I also expect, my best guess is that after that has happened, the water that was initially ice, let me call it ice water. This water, which was initially ice, will gain heat and temperature increase from 0 degrees Celsius to final temperature. This is my guess. So after analyzing it like this, I can now use our conservation of energy. The conservation of energy principle that we used last time, where the heat that is lost by one is equal to the heat that is gained by the other. I have already identified here who is losing heat. The only one that is losing heat is the water. This is the only one that is losing heat, and its temperature will increase. So I am going to talk about the heat capacity of water, mass of water, times the change in temperature of water will be equal to, I have already identified that part of this heat will go towards increasing the temperature of ice from minus to that. So this is going to be equal to the heat from minus 10 ice, from minus 10 to 0, plus part of that heat, of this heat that is being lost, is going to be go towards the latent heat of fusion. Part of that heat which is being lost by the water is going to now be part of increasing heat from ice water from 0 to infinite. This is what we have identified. So for me to be consistent, let me also just use a symbol here. And the symbol I'm going to use is Q from 87 to P is being shared. Part of it will go towards increasing the temperature of ice. Part of it will go towards changing ice into water. Part of it will go towards changing the temperature of ice water from 0 degrees to 5. Then I can now use our formula using the fact that Q is equal to C M or no Cm times, using the fact that is equal to Cm times change in temperature, and the fact that Q, this is Q for latent heat and Q for calorimetry, Q for latent heat is equal to ML, like this. Michael, hand is raised.
Oh, sir, I'm asking if you can kindly repeat on how the heat to be distributed.
You can see the formula. If you just
I
check
can
up
see it,
here,
but
if you check up here, we already identified that when the heat is being lost by the water, some of it will increase the temperature of ice from -10 to 0. Part of it will change the phase of ice from solid to liquid. Part of it will increase the ice that was the water that was ice from 0 to final temperature. So these statements here, we have just expressed them into the heat that is lost. The heat that is lost is being used to increase the temperature of ice, is being used to change phase from ice to water, is being used to increase the temperature of that ice, of that water which was initially ice, from 0 degrees Celsius to the final temperature. It's just as straightforward as it is. When you just look at that equation, it will help you realize that whatever we've lost, it's like you have 100 kwacha, you go to town, you start breaking down how that 100 kwacha was used. You can tell yourself that I used part of it, the 100 kwacha, I used part of it for transport, part of it to buy sugar, part of it to buy eggs. That's exactly what we are doing. It's just the same as the way we spend money. We always identify how much money did I have and where has that money been used. That is the principle that we are using here. So that's what we've done here. And so we are now using these two formulas here. In using these two formulas, we are going to replace this one here. It's about change in temperature. So change in temperature has to do with heat capacity of water, mass water, times the change in temperature of water. This is equal to, this also is about change in temperature from 0 to -10 to 0. So this is about heat capacity of ice, mass, ice, and the change in temperature of ice. Plus, this is about the change of phase. So we are going to use the equation that deals with change in phase. So we have mass, ice, and latent heat capacity, ice. Then this one here is about change in temperature from 0 degrees Celsius to final. So here we are going to have heat capacity of water multiplied by mass of ice. I'm calling mass of ice here because this is the same mass that was initially ice. Now it has become water, but I'm using heat capacity of water. I want to make sure I am identifying, because there are two kinds of water here. There is this water which was at 87 degrees. There is now additional water that has melted. It was originally ice, now it has melted. I want to differentiate this water and this water. Times the change in temperature of ice water. So let me put it like that. Once we have this now, we can put the full equation where we have C of water, M of water, T of water minus T. I know I explained to you how we do this. We always look at the higher one, minus the lower one is equal to C of ice, mass of ice, and we have 0 degrees. So let me put the same 0 degrees. Multiply by 0 degrees minus negative 80 degrees minus negative 30 degrees. Then plus mass of ice multiplied by latent heat capacity of ice plus specific heat capacity of water multiplied by mass of ice. Here we have T final minus 0, like that. So this is how it is all going to happen. The next thing now is you are looking for T final. So we are looking for T final, this and this. You can then expand this equation the same way we did with our previous equation, where we are going to have T water, M water, T water, minus T water, M water, T final is equal to C ice, M ice. This 0 here is going to go, so I'm going to remain with 30. Then I have plus M ice, L ice. Okay, so I'm in a place where network is a challenge, far away from your civilization, you guys. So please forgive my situation. But I pray that now we don't get another disturbance. Okay, we have continued to record. Anyway, the good thing is that all the recordings are being saved properly. Yes, Ignatius Ntasha.
So I wanted to ask, in the equation, where is negative 30 coming from?
Negative 10, I mean. You could have just corrected me to say that it was negative 10 and not 30.
Okay.
So this is negative 10. Negative 10 degrees. And here we are at negative, this is 10. So it is 10, no, not negative 30, but 10. Okay, so here we're talking about C, water, M, ice, T, final. When we multiply this by that, we have 0. So we end it there. And so the easy thing here is we are going to take this to the other side of the equal sign, and we move these to this side and this to that side, so that we have C water, M water, T water, minus C ice, M ice, N plus, no, minus M ice, L ice. This is going to be equal to C water, M ice, T final. We get this, it's the negative. When we take it to the other side, it becomes plus C water, M water, T final. So in 10 minutes, we are going to have a short break. Then we are going to continue after we break a bit for 10 minutes. So this is what we've done. I just moved this to the other side and I moved that one to the other side. Then I have now got these whose which are unknown. We have C, water, M, ice, plus C, water, M, water multiplied by C. I know this is equal to C, water, M, water, C, water minus C, ice, M, ice multiplied by 10 minus M, ice, L, ice. Like this. Then I can divide this side by C, water, M, ice, plus C, water, M, water. I also divide this side by C, water, M, ice, plus C, water, M, water. This will cancel with this, but it will remain on this side. I'll remain with only P final here. Then you can now add C water. You can find it in the textbook. M water is given as the 7 kilograms. C water is 87 degrees Celsius. C of ice, you can find it in the textbook. M ice was given as 4 kilograms. N is a number. M ice is 4 kilograms. L ice is given in the textbook. Go to the textbook tables and find it. Replace here, and you are going to find the final there. So we have seen how the equation, basically, we were seeing how this equation here will not only involve two things, but it will involve one thing losing and the heat being used for different processes. So it's always important for you, when you read the question and you have visualized it, you must identify which substance is losing heat, and after it has lost heat, which substance is gaining heat. And when that heat is being gained, for what process is it being used? Once you identify all of these, then you are able to now break it down that the heat that is being gained is being used for that, and for that. This is the heat that is being lost by one substance. It is also possible that there are two substances losing heat and there are many other substances gaining heat. Here we're looking at two substances and they were just different processes. It's also possible that we have different substances gaining heat. The reason why we only talked about ice here and water is because the question was very clear that water is in a bucket made of styrofoam. One property of styrofoam is that styrofoam is an insulator. It does not allow transport of heat. So it means that all the heat that is coming from the water is being used to increase the temperature of ice and also melt the ice and increase the temperature of the water that was originally ice. Styrofoam is not receiving. But if we were told that the container of the water is made of copper, for example, or silver, for example, we were going to also talk about the heat that is being gained by the silver. So here we are going to have an additional thing where the silver, which contains the water, is also gaining the heat. So in this case, we only have two substances exchanging heat and not more than two substances. Let us do a quick example, which I'm going to give as your own activity to do on your own to practice what we've just done together. another example. I'm going to write it down before we break for because of the Zoom that will allow us to break. We have a 3-gram lead bullet. At 80 degrees Celsius is fired at a speed of 240 meters per second into a large block of ice. In which it embeds itself. What quantity of ice melts? Or how much ice will melt? So in this case, we are assuming not the entire block of ice will melt. Only part of the ice is going to melt. The situation here, you have a bullet that is moving at 240 meters per second. And it meets a huge block of ice, and then it embeds itself inside here. And then you are asked how much ice melts. And here, let us assume the kinetic energy is converted into, let us also assume that kinetic energy becomes thermal energy. So assume this. We're just going to assume this. But in the test, I will not give you this. I will let you guess on your own. Make your own assumption. But here, you assume this is the case. So now, this question, you are going to solve it on your own. And then we will see as a practice. And then if you have any challenges, you can ask me and we can discuss it together. Okay. So rather than us being disturbed after 1 minute, let me stop the class. And when I stop the class,